Chapter 4, we're taking a look now at motion in 2 and 3 dimensions. So now that we've had chapter 3, where we got to see vectors, that understanding will help us to analyze what we did in chapter 2, where we just had motion in 1 dimension, in now a more interesting way, studying motion in 2 and 3 dimensions. So it will just be really an expansion of chapter 2 in light of what we've learned in chapter 3. So our first section is section 4.1, looking at position and displacement and how we can describe those variables in 2 and 3 dimensions. So a position vector is a way that we can locate a particle in space. It extends from a reference point, which is typically the origin, to wherever that particle is located. We can locate it that way, right? So our r vector would be the position vector. It's equal to the x coordinate times I hat plus the y coordinate times j hat plus the z coordinate times k hat. Right, where the x, y, and z are just the scalar distances, and then the unit vectors specify the direction of it. So for example, you could imagine a position vector for the position of -3 meters, 2 meters, 5 meters. Well, if we want to write that as a vector, we add in our unit vectors there. So it becomes r hat is -3 meters I hat, similarly for the j hat and k hat components. And this figure, I'm sorry, it's a little bit small, but it depicts it really well. We have the x direction going horizontally here, the y direction going up, and the z direction coming out of the page. And so for the x direction, we know it's -3 meters I hat. So because it's this -3 meters in the I hat direction, instead of being along the positive x-axis, it is in the negative x direction, and that's that -3 meters. Similarly, we have 2 meters in the j hat, so if this is our y direction, then it's going to be going parallel to the y direction, going up. And finally, we could fill in with the 5 meters in the k hat direction, where k hat is the z direction coming out of the page. And so that is coming out here to this point. And when we add these 3 individual vectors together, that gives us the overall resultant vector, as is shown with the r vector here. So thus, we're able to locate this particle that's hanging out in space here and able to describe exactly where it is relative to some point. Now, once we know the position, we can look at changes in position, which any change in position is known as a displacement, right? So we saw displacement already, and that was delta displacement, right? The change in position is the final minus the initial. But here we're just adding the arrows because they're now vectors. And because it's a vector, we can rewrite this in terms of the scalar components, in terms of x2 minus x1 in the I hat direction, plus y2 minus y1 in the j hat direction, plus z2 minus z1 in the k hat direction. Or more compactly, we could instead write it in terms of the changes for each of those coordinates. So the displacement vector can be written in terms of the displacement in x times the I hat plus the displacement in y times the j hat plus the displacement in z times the k hat, just specifying each of those directions, and they are independent of the other directions, which is a key detail we're going to see in the time to come. But for now, we're going to use this displacement, and that's going to be key as we take a look at our next section. So stick around.